We are gathered here today to celebrate a momentous occasion. Unit 18, Electrochemistry, is the final unit of the AP Chemistry curriculum. So we are really on the home stretch now. The unit itself is kind of an oddball, deals with electricity, which is not something we really talked about at all this year, deals with some oxidation and reduction reactions, which we have talked about, but in a completely different context, and has some of the longest stoichiometry problems we're going to do all year. Okay. Overall, the chapter is relatively short. Let's get started. All right. The unit is called, like I said, electrochemistry. The main things we'll be focusing on balancing redox reactions, which don't panic is not like how we balanced them before back in like unit 4. Okay. This is a little bit simpler. We're going to talk about galvanic cells, which are basically like batteries. We're going to talk about how they work. Cell potential, concentration of cells, and electrolysis. So, a couple of terms we need to know from previous units have to do with oxidation and reduction. An oxidation reduction, or we shorten it to redox reaction, involves a transfer of electrons from the reducing agent to the oxidizing agent. Okay? But the main thing focus on is a transfer of electrons. Electrons are moving from one species to another. Okay? The oxidation is the loss of electrons. If something is oxidized, that means it loses electrons. For something to lose electrons, something else must gain them. My electrons can't just disappear. So the reduction is a gaining of electrons. A redox reaction, one thing is oxidized, one thing is reduced. Can't have one without the other. Our mnemonic to remember which one is which is Leo the lion says grr. Lose electrons, oxidation. So if something's losing, it's oxidizing. Gain electrons, reduction. Okay, here is a chart we're going to be using for basically this entire unit. This is a series of standard reduction potentials. If we look, all of these different reactions, we're starting with something here on the left, adding electrons. You'll notice the whole way down, that's what we're doing. Adding 1, 2, or 3, or 4 electrons. Okay, gain electrons is reduction. So this is a chart of reduction potentials. Basically, how much electricity, you can kind of think as a simple way to think about it, but how much voltage is produced when this thing reduces. Okay. Voltage is basically a measure of the pressure of electricity, but basically just think about it like electrons are moving from one place to another. When these electrons move in this chemical reaction, it makes this much voltage. And we think about voltage, think about like a battery. You have like a 9-volt battery or a 12-volt battery. The higher the voltage means the stronger the battery, right? Essentially. And that's what all these are. So if F2 gains 2 electrons, it produces not a current, but like a voltage of 2.87 volts. Electricity vocabulary is really strange. We don't use it a bunch in this class, so we haven't really learned the difference between like current and voltage and all these different terms. And they're not super important, but this one is in voltage. Okay. So you'll look as you go down, these are getting lower and lower and lower. Eventually it gets to 0. Okay. And then it goes lower and even into the negatives, some really low negative numbers even. Okay. That's because all of these reactions, if you check a chart, will all be written as reductions. Okay. But some of these aren't producing a positive voltage when they're reducing. They're actually making a negative voltage. So we'll kind of get into that. The standard way to write this table is everything's written as a reduction, even if it's generally a better oxidizer. A misleading part of this unit, as you go up on this chart, follow this red arrow up, they get better and better at reducing, which is why the standard potential is getting higher and higher and higher. Okay? And as you go down, they get better at oxidizing. But if you read the little arrows here on the left, it says the opposite. It says as you go up, you get a stronger oxidizing agent. And the word agent, I want you to think like a double agent, right? Who's trying to like betray somebody. And it's trying to betray common sense today. Okay? So agent means the opposite. So an oxidizing agent is something that's good at reducing. A reducing agent, something that's good at oxidizing. This language is used kind of frequently in practice problems and on like things like Albert practice, or I've seen it on Khan Academy. It's language that used to be really important for the AP exam, but they've actually recently cut it. Okay. So we're not going to use it exclusively, but if you see it on a chart like this or something, you should know if you see the word agent, it actually means you're doing the opposite thing. So oxidizing agent means it's good at reducing. So as you go up, the reduction of these is getting better. And as you go down, the oxidizing is getting better, even though the chart is trying to lie to you. We'll come back to this table. We'll need these half reactions and the numbers associated with them to solve some problems. We're solving problems about cell potential. Cell potential is another way to say voltage or electromotive force. All these things kind of mean the exact same thing. A galvanic cell, galvanic cell kind of means just like battery. We're going to show you a drawing of a galvanic cell in just a minute. It consists of an oxidizing agent in one compartment that pulls electrons through a wire from a reducing agent in the other compartment. Electrons are moving from where we're going to learn the negative terminal of a battery to the positive terminal. And that pull, how strongly those electrons are being pulled through that wire, is the cell potential or voltage. So when you think about voltage, that's really what you should think about. Voltage is how strongly the current is being pulled through, or the electrons are being pulled through the wire. All right. The unit of electric potential is the volt. We usually just write a capital V. Down here's a more like a SI unit definition. 1 joule of work per coulomb of charge transferred. Don't worry about that. If you're physics, worry about that. All right, the instrument used to measure cell potential is called the voltmeter, which is aptly named, which works by drawing current through a known resistance. A voltmeter will measure a potential that is less than the maximum cell potential because the frictional heating that occurs wastes some energy. Okay. What the second sentence here means is that a voltmeter measures how strongly the electrons are being pulled through a wire, but it can't be perfect. Okay. As electrons are pulled through a wire, some amount of heat is lost due to friction and lost to the environment. So the voltmeter technically measures slightly less voltage than is actually there, but it should be negligible in most cases. All right. So standard reduction potentials. An oxidation reduction reaction is always broken down into 2 half reactions. To balance redox reactions before, we broke them into half reactions, balanced them separately, then re-added them together. Therefore, it'd be convenient if we could assign a potential to each half reaction, a voltage of each half, so that we can calculate the overall cell potential just by summing up the 2 potentials of the 2 half reactions. All right, so for a full redox reaction, you're going to have 2 of these half reactions together. We have the voltages here of 1 half, and basically what we're going to do is just add together the numbers to get the voltage of the entire reaction, and it's really convenient. There's only like 1 or 2 little catches we're going to have to worry about. Our formula we need here, E of the cell, has this Greek letter epsilon. You can also just write it with a capital E. You'll see it both ways. But this is the voltage of the cell, or the cell potential, is equal to the oxidation potential half reaction plus the reduction potential half reaction. Add those 2 numbers together, and you get the entire voltage of the entire cell. Okay. If these numbers seem like they're coming from nowhere, like I'm talking about these numbers on the chart, they're basically just all compared to kind of like a 0. We kind of like zero out like you would like a scale when you're measuring something, right? If you want to measure the weight of like some solid, you're not just going to throw the solid on the scale because then it's going to make a mess. You're going to like put a beaker on there and then zero out the scale, then add some solid to measure it. And that's basically what we've done here. Our baseline reaction is this 2H plus 2 electrons gives you H2, and that's exactly 0. So we're comparing the voltage of this to all the other reactions. So like this isn't like a flat 2.87, it's just 2.87 above hydrogen, which is kind of our standard. Not really important, but just in case you see something about that. In order to facilitate this process, the standard hydrogen electrode, which has a half reaction of 2H plus 2 electrons, gives you H2, was assigned that potential of 0, and it's the standard by which all other standard reduction potentials are based. They will always have these values: 25 degrees Celsius, 1 molar concentrations, 1 atm of pressure. There are some advanced formulas you can use to calculate them when they're not at standard potentials. not at standard conditions, excuse me. We're not going to go over those in this video, though. We're just going to assume all these things are always true. If it says otherwise, there's a couple equations you can use. Okay. So all half reactions, like I was saying before, are given as reduction processes in the standard tables. These standard reduction potentials can be manipulated, like the half reactions, to balance out the electrons on both sides. Okay. So when a half reaction is reversed, if you flip the operation around, the sign of the voltage is also reversed. So if you have to take any of these reactions and flip them around, so let's scroll back to the reactions. If you flipped this reaction backwards, so you started with 2F minus, and you made these two things as your products, then you just have the same potential but opposite sign. Okay. So if you need to flip any of these reactions around to balance them out, then you just make the sign negative. If you need to multiply one of the half reactions by an integer, now this can be confusing. So to make the electrons cancel out, which we're going to talk about in a second, you might need to double one side. If you do that, the voltage actually stays exactly the same, which can seem misleading, but if you think about it, you're doubling the reaction, but you're also doubling the amount of electrons that you need. So the pull on each individual electron is staying constant. You're doubling the voltage while also doubling the amount of things being pulled, so it kind of cancels out. So if you have to double something, it actually stays exactly the same, which is convenient, but can be confusing for sure. A galvanic cell runs spontaneously in a direction if you have a positive E. So we talked about spontaneous with Gibbs free energy. A negative Gibbs free energy, a negative G, means something is spontaneous, but a cell is going to be spontaneous if you have a positive E. So if the voltage of the overall cell is positive, that means this reaction will happen. If it's negative, it's not, which makes sense because you can't have like a negative 1 volt battery or something like that. That doesn't make sense. Okay, so here we have a galvanic cell. We have a battery based on the following two half reactions. Okay, so these are two half reactions. It's written the voltage for us. These might be in that data table above. I don't remember. But you'll always have to be given this information. You wouldn't know this number without it being provided. So what we want to do with this is I want to get the balanced cell reaction. So first we're going to basically balance this redox reaction, and then we're going to calculate the standard potential of the cell. Okay, so what we've said before is that a reaction is always made of a reduction and an oxidation. You can't have one without the other. But both of these are written as a reduction because all half reactions are written as a reduction to keep it standard. Okay. Well, whichever number is higher, so more positive or overall larger, okay, which in this example would be this first one, would be gold. Whichever number is higher is the one that will reduce. Whichever one happens to be lower, which is lower on that chart, or a more negative number, is actually going to flip around. We're going to, instead of doing the reduction of this is going to become the oxidation step. So whenever you have a problem like this, they'll always be written like this, as two reductions. You have to analyze them, figure out which one will reduce, which one will be the oxidizing one. Whichever number is higher is the reduction always. It's better at reducing, so it's going to be the one that reduces. Whichever one is lower is better at oxidizing, so instead it's going to oxidize. Okay, so let's take a look here. I have my two reactions I'm going to write. I'm just going to copy them down to start. Okay, my first one has a voltage of 1.5. Now my second one here has a lower voltage than that. Its voltage is negative 1.18, so it's definitely lower. Okay, so the top one, I'm going to make this one the reduction because it's better at reducing. It's a higher, more positive number. So I'm going to leave this one entirely unchanged. But this bottom one is going to be my oxidation step because its number is less. Okay, but it's not written as an oxidation. So I'm going to flip this reaction around instead. Now, when I flip it around, its voltage is now going to flip as well. So voltage has become a positive 1.18 when you write it this way. So we don't need that anymore. This is what our oxidation will look like. This is the most important trick when you do any sort of problem like this. The oxidation step, you're going to flip it around and write it as an oxidation. Remember, lose electrons oxidation. I'm starting with manganese, and as I go to the right, I'm losing electrons. These electrons are leaving. Up here, I'm gaining electrons because I'm taking my reactant and adding extra electrons to it. Okay. Well, I want to now go ahead and first, actually, I'm just going to calculate the cell potential. Okay. You don't have to do the balance reaction first for this. So the cell potential is the E of the oxidation step plus the E of the reduction step. I can just go ahead and solve this. I know what these values are. The oxidation step, remember to use the flipped sign, so 1.18 regular, plus the reduction sign, 1.50. And we're just going to add those together. And that's that answer. Easy as that. The reduction number stays the same. The oxidation number gets flipped. All right. Now I'm going to take these two reactions and I'm going to balance them. Right? I need to make the electrons cancel out because you can't write electrons in overall reactions. So to make that happen, there's a 2 and a 3, which is a little bit annoying, which means I actually will have to do like some least common factor stuff. If I can make them both equal 6, they can cancel out. So this top one, I have to double everything. The bottom one, I'm going to have to triple everything. Remember, when I double or triple this, voltage doesn't change. That's why we could have solved this already. We don't even have to worry about the balanced reaction to find the cell potential. Okay, so I'm going to do this top one. I'm just going to rewrite it down here. Plus 6 electrons gives you 2 regular golds. I'm going to write the next one down here. 3 manganese gives you 3 manganese 2 pluses. Remember to double everything. Those are our two reactions. Electrons, one on the left, one on the right. Both are 6. Cancel out. Everything else we just add back up. So I have 2 Au3 pluses and 3 manganeses total on the left side of my arrow. And on the right, I have 2 golds plus 3 manganese 2 pluses. And that is my balanced cell reaction. If I check, the number of atoms on both sides should be identical. So I have 3 manganeses, 2 golds on each side, and my total charge on each side should also equal. So this is 2 times 3 plus is 6 plus. This is 3 times 2 plus is 6 plus. So that's a properly balanced reaction. And that's the cell potential of that balanced reaction. Okay, so let's talk a little bit more about what a galvanic cell looks like. It's a device in which chemical energy is used to changed to electrical energy. We're going to use these chemical reactions to make electricity, basically. This uses a spontaneous redox reaction to produce a current that can be used to do work. Here is what it looks like. And if you've been doing any practice tests and seeing drawings like this, they're always going to be pretty much set up exactly like this. There's a lot going on here. So let's start with each of our 2 beakers. So I have a beaker on the left and a beaker on the right. This beaker is filled with zinc sulfate. Now, I don't care about zinc sulfate itself, but this is going to dissolve. It's going to make zinc ion, zinc 2 plus specifically, and sulfate ion. The sulfate's not going to matter at all, but I am curious about the zinc. So it's going to make some zinc 2 plus. I have a zinc bar immersed in this solution, or submerged in this solution. Over here on the right, I have a copper sulfate solution. So again, I don't care about the sulfate, but I do care about the copper. It's going to make some copper 2 plus ion, and it's going to be a bar of copper submerged in here as well. Okay, so I have basically 2 beakers that look pretty much set up with a bar of metal that matches the ion in the solution. Then I'm going to take a little wire and run it from one bar to the other. I'm going to put a voltmeter in the middle just to measure how much voltage is being pulled. And then the last thing I have going on here is the salt bridge, which the salt bridge helps to connect the whole thing, like it all has to be connected. And it also is going to provide ions, positive or negative charges, to these things, to these solutions as needed. Okay, so kind of running through everything in this picture. There's a lot of stuff. Just to give you a little preview, this is what it's going to look like. Okay, so we're definitely going to go over this in class because it's easier to talk about it and draw it all together. But we're thinking about, when we look at a picture like this, the journey of the electrons through this picture. The movement of electrons is what's making voltage, is what's making this battery operate. So first thing we're going to do is compare these two half reactions and see which one will be the reduction, which one will be the oxidation. We're going to check our reduction potential chart. The higher one will be the reduction. The lower one will be the oxidation. So I'm comparing copper 2+ and zinc. Copper 2+ is here. It's a positive 0.34. Zinc is down here. It's a negative 0.76. Copper is higher. It is going to reduce. Zinc is lower. Therefore, it's going to oxidize. The picture has that labeled already. This is the oxidation side because that's my zinc, lower on my reduction potential chart. Over here is my reduction side. That's where copper is. They've already gone ahead and written the two half reactions below correctly, though. So over here I have copper reducing, meaning gaining electrons. And over here I have zinc oxidizing, which means losing electrons. Oh no, they did not write it correctly. Okay, so what we would do is flip this one around. We'd write zinc 2+ turning into zinc and 2 electrons. Okay. Okay, this is a bit of a typo here. So pause 1 moment. Okay, so I corrected it real quick. Here I flipped it around, okay? So we have zinc solid is going to split apart into zinc 2+ and 2 electrons. All right, so let's think about what's happening in this entire picture overall. So we're going to start on the oxidation side. You'll notice we called it the anode. That is the nickname for the oxidation side. The way to remember this is with another mnemonic. This starts with an, this starts with ox. So you think about an-ox, and ox goes together. You have to call it an-ox because this is an O, so you have to make it an and not a, right? Over here on the right, we have reduction side, which is called the cathode. So the way to remember this, red cat. Red and cat go together. They also have a charge. The anode is the negative side, just like anion means negative charge, anode means negative. Just like cation means positive charge, cathode means positive terminal. We're always going to start at the oxidation, the anode side, the negative side. Electrons always start at the negative and move towards the positive because they're attracted to positive charges. Okay? So over here, I have my zinc. And according to this reaction here, it's going to split apart and make some zinc 2+. Well, the zinc 2+ is just going to go into the solution. There's already some zinc sulfate here, so you're just going to add some more zinc pluses down here. The 2 electrons are going to leave. They're repelled from this negatively charged node here, and they're going to move along the wire this direction. You can kind of see the electrons moving this direction. And they're going to move over to the positive side. As they do, they pass through the voltmeter, which lets us read how much force or how much pressure those electrons are putting on the voltmeter, on the wire. The electrons arrive over here in the positive terminal. And the reaction that happens here is you have some copper 2+, which are floating around in this blue liquid, adding to some electrons. Well, I just added some new electrons from this wire. They're now hanging out on this bar. And then it makes solid copper. So what's going to happen is as the electrons are entering this bar, they're going to combine with the copper 2+ in the solution to actually make more just regular solid copper. So over time, this copper bar is going to get bigger. We're going to add more and more copper atoms to it. This zinc bar, if we think about its size, it's a reactant over here. It's going to be breaking apart slowly. It's going to be disintegrating a little bit at a time. Right? It's falling apart because it's losing zinc 2+ into the solution, and its electrons are leaving through the wire. So over time, the negative terminal will actually start to wear out and corrode a little bit, get smaller and smaller, and the positive will start to deposit or plate whatever metal it has on it. Last thing we need to talk about is the salt bridge. So the salt bridge is there to help the battery last longer, basically. And this left side over here, I'm adding Zn2 pluses to my solution. Well, we're going to try to neutralize that a bit. Eventually, that'll make this have a more positive and positive charge, which I don't want because this is my negative battery terminal. So if I keep putting it in a positive solution, my battery will stop working. So to keep this solution negative, the negatively charged anions from the KCl, which will be the Cl minus, will travel through the salt bridge over into this solution to help keep it negative. This solution over here is losing copper 2 plus ions. They're going into the bar. So you're losing some copper 2 plus. So this bar it's getting more negative over time, but it's the positive node. So you don't want it to get more negative. So the positively charged portion of the salt bridge, the potassium in this case, are going to go through the salt bridge into this solution to help keep it more positive. That's kind of all the stuff that happens with this sort of reaction. Now to summarize, oxidation occurs at the anode. Reduction occurs at the cathode. The salt bridge is there. It's a device that allows ions to flow without extensive mixing of the solutions. The salt bridge contains a strong salt that provides cations and anions to the solution. Now, here are all the differences between the two sides, between the anode and the cathode that we started to talk about. So the anode, the left side in our picture, supplies electrons to the circuit. Right? They're the supplier of electrons. It's the negative pole of the battery, the site of oxidation. It's written on the left-hand side in line notation, which we haven't talked about. And it'll be the half cell with the lowest standard reduction potential. The right side, the cathode, accepts electrons from the external circuit, the wire. It's the positive pole of the battery and the site of reduction. It's going to be written on the right-hand side in line notation, which we'll talk about. And it's the half cell with the higher electrode potential. So those are kind of the things we need to know about that drawing. And there's a lot. Now, we're talking about line notation. It's kind of a dumb shorthand way to write the reaction, the redox reaction occurring in a galvanic cell. So it looks like this example here at the bottom. So you basically split the half reactions into two. You're going to write the anode component on the left, which is the oxidation. So whatever the oxidation is happening, right? Oxidation is losing electrons. So this thing should be losing electrons or getting more positive. Write that on the left side, separate them with a single line. So put a double line in the middle to represent that this is the other part of the battery now. And you put the cathode on the right. So you put the reduction step, Au3+, gaining electrons to become neutral Au, right? Neutral gold, is on the right. So the description of a galvanic cell includes all these things I was just mentioning. I know it's a lot of words without writing them all down, which can be tricky, but this is definitely something we're covering in class. Okay, you include the balanced cell reaction, the overall cell potential, designation of each compartment as the anode or cathode, the direction of the electron flow, the nature of each electrode, meaning is it positive or negative, the ions present in each compartment, and the line notation are all things that can be used to describe a galvanic cell. Right. So for the previous example, we've already done the balanced cell reaction, the cell potential, the line notation. Oxidation occurs in the manganese compartment, so it's the anode. Reduction occurs in the Au, so it's the cathode. The electrode in the anode is solid manganese. The electrode in the cathode is solid gold. The electron flow goes from a compartment containing manganese, since it loses electrons, to the gold compartment, since it gains electrons, from anode to cathode. Right. And here's the concentrations. We're assuming they are standard 1 molar solutions of each. Okay. All right. If either the oxidation or reduction reactions consist of only aqueous or gaseous substances, then we must use an inert metal like platinum to act as the anode or cathode. For example, in this reaction, this is written in a stupid way. Right? We're not going to do anything like this. But something like only aqueous solutions, if you can't use a full bar of solid iron 2+, because that doesn't exist, for example. Then we use some sort of other inert substance, which means it doesn't react with anything, like platinum. Platinum is very non-reactive and very strong. That's how you'd write that in line notation. Okay. As the cell discharges and current flows from anode to cathode, the concentrations will continue to change, and as a result, the standard potential of the cell will continue to decrease until it reaches equilibrium. At that point, the two cell compartments will have the same free energy. So the delta G is equal to 0, Q is equal to K, and the energy of the cell is 0, meaning the battery is dead. So these are all different ways to say your battery's died. Right? You're non-spontaneous anymore because your delta G is 0. Your Q equals your K, which means you have reached equilibrium. And the energy of the cell voltage is 0. Those are all different ways to say the reaction is done. Over time, this battery will begin to wear out. All batteries die. So back to the picture, 2 ways this battery can die. One, like we said, this zinc over time is starting to fall apart. Right? So I can run out of zinc because it is all being dissolved into zinc 2+. Or I could run out of salt bridge, right? The K and Cl could eventually run out and be unable to help keep my charges negative and positive. And over time, just naturally, the negative will start to wear out, the positive will start to wear out as electrons start to go, and eventually the battery will die as it reaches equilibrium. Okay. Last couple things to talk about, we have to talk about electrolytic plates or electrolysis. Now, the cell we just talked about is called a galvanic, sometimes called voltaic cell. It produces current when a redox reaction proceeds spontaneously. Now, an electrolytic cell uses electrical energy to produce a chemical change. So it's kind of the backwards of what we were just talking about. The process of electrolysis involves forcing a current through a cell, so we're adding electricity to stuff to make magic happen, to produce a chemical change for which the cell potential is negative. This is electrical work. That is, electrical work causes an otherwise non-spontaneous chemical reaction to occur. We can use electricity to make a reaction that shouldn't happen, which we'll talk about what those look like. So this is basically the opposite of what we just did. We use chemistry to make electricity happen. Here we're going to use electricity to make chemistry happen. All right, so we're going to do some fun stoichiometry. We're going to consider the stoichiometry of electrolytic processes. That is how much chemical change occurs with the flow of given current for a specified time. Now, current's not something we've talked about very much or at all. It is the measure of how fast charge can travel through a wire. The bigger the current, the faster you can imagine them traveling. It's kind of related to velocity. It is measured in amps, which is A, which are equal to coulombs per second. Coulombs is a unit of charge. How many coulombs pass through my wire per second? All right, the problem will look like this. What mass of copper is plated out? Now, reading down from this paragraph here, plating refers to the deposition of the neutral metal on the electrode by reducing the metals in the solution. Basically, I'm going to be adding atoms to my electrode, to my piece of metal. Okay, so I'm going to take basically a piece of metal and place it in a solution of copper 2+ and pass electricity through it. And over time, that copper 2+ in the solution will change into just regular copper. It's going to reduce to form standard copper. Okay. So we have some information here. Let's go ahead and gather this and then talk about what we're going to do. So basically what's going on here, I'm taking an electrode and I'm going to run some electricity through it, run a wire through it. The wire is there to supply electrons. So I'm going to have some extra electrons chilling on my bar as they go from left to right in the solution. Now my solution has some copper 2+ ions floating around in it. Our reduction reaction says copper 2+ reacts with 2 electrons to make standard copper. So these copper 2+s are going to see these electrons on this bar, react with it to make standard copper. And now that standard copper is actually just going to stick to this bar. And we're just going to add copper. We're going to plate it by adding new copper atoms to this bar over time. What we're going to calculate is exactly how much copper are we going to be able to make. We're going to run a current. Our current's going to be 10 amps. An amp is a coulomb per second. So you can think about that either way. We're going to run it for 30 minutes. We're going to run the electricity and see what mass of copper we're able to plate out. So what we're going to do here is we're actually going to do some train tracks. We're going to do a stoichiometry problem. So we're actually going to start with the amount of time. That's the variable that we're changing. That's the number from the question. We want to go from 30 minutes, convert it into grams of Cu, which sounds weird. So let's talk about how to do that. We're going to start with 30 minutes, and we're going to convert that into seconds. So 1 minute on the bottom equals 60 seconds on top. Well, how are seconds involved? Well, we have this information about the current. Current is coulombs per second. So this is telling me how many seconds I've been active for, this solution setup's been running for. I can use that to find exactly how much charge, or coulombs, have passed through my wire. Seconds is on bottom. I'm going to cancel it. I'm going to put coulombs on top. So my numbers here, 10 coulombs pass through the wire every 1 second. So that's our first goal here. We're actually calculating exactly how much charge has passed through that bar over the entire duration of 30 minutes. All right, well, how is that going to be helpful to us? Well, we have a constant to use for that. So we've calculated if you add up 1 mole of electrons. That's a lot of electrons, right? Each electron has a charge of about 1.6 times 10 to the negative 19 coulombs. Remember that 1 mole of electrons is 6.022 times 10 to the 23rd electrons. So if I want to see how much total charge that equals, I'm just going to multiply these two numbers. This is the charge of a single electron. This is how many electrons I have in 1 mole. And the number comes out, I think it's like 96.485 coulombs per mole of electrons. So that's our next goal. We know exactly how many coulombs have passed through. I'm going to change that into moles of electrons. Coulombs is on bottom, moles of electrons on top. 1 mole of electrons has this number, 96.485 coulombs. This is a special number called Faraday's constant. And this is how we calculated it. All right. Well, that's telling me exactly the number of electrons. So what we've done so far is over 30-minute interval. This, if I just solved it like this, would tell me exactly how many moles of electrons have passed through my wire. Okay. Well, we have this reaction to use. I can convert moles of electrons. If I have so many moles of electrons, I can convert to find out how many moles of copper I was able to produce. That's what we'll do next. Moles of electrons on bottom to cancel. Turn that into moles of copper. Do a mole-to-mole ratio using this reaction. So the numbers from the balanced equation, I have a 2 for moles of electrons, so I'll put that on bottom. Copper has no number, which just means 1. That'll go on top. This tells me how many moles of copper I've produced, because it told me how many moles of electrons I had to start with. Now my last step here, go from moles into grams. What's the molar mass of copper? Gotta Google 1 second. Okay, it's 63-ish, 0.5, let's just write that, grams of copper per mole. That's my full stoichiometry setup. Minutes into seconds, seconds into coulombs using the current of 10 amps. Once I have coulombs, I can actually find out exactly how many moles of electrons have traveled through my wire. Use that to find how many moles of copper I was able to produce, and then just turn it into grams. All right, a lot of math here. So I got 30 times 60 times 10 times 63.5. We just rounded, so that'd be okay. Divided by 96.485, divided by 2. 5.92 grams of copper. Which doesn't seem like a lot, but that is basically copper I was able to make to appear just basically out of nowhere, out of this liquid. Which is pretty cool. All right, now our last question here. We're going to see what mass of copper is plated out. It's the same question. What happened? Okay, there we go. Last question for real. how many minutes must a current of 5 amps be applied to a solution of silver plus to produce 10.5 grams of silver metal? So this looks like the same problem but backwards. Okay? So I'm taking, this time I have 10.5 grams of silver. I know how much I make. So how much time must pass? And it's asking for minutes. So how many minutes does it take to do that? We have the same setup. We're going to do the same math problem. Our equation's a little bit different this time. Some different numbers, but it gives us that, which is good. So we're just going to start solving. Now we're doing the flipped version of what we did last time. So I'm going to start with 10.5 grams of silver. I'm going to turn that into moles of silver. So that's about 108 grams of silver for 1 mole of silver. And then we're going to kind of go through those backward steps. I'm going to turn moles of silver into moles of electrons. This time, fortunately, we just have a 1-to-1 ratio. So just put a 1 on each side. Moles of electrons we're going to turn into coulombs using that constant from the last problem. There's 96,485 coulombs in a mole of electrons. Okay, now I need to turn coulombs. It gives me 5 amps, which means 5 coulombs per second. So I can use my coulombs to find how many seconds the wire must have been running for. Coulombs on bottom, I have 5 coulombs every 1 second. Now, if I was just asked for time, I could stop there, but I do want minutes, so I'm just going to put 60 seconds equals 1 minute. All right, let's solve this now. 10.5 times 96,485. Those are all 1, so I don't care. Divide by 108, divide by 5, divide by 60. And it's 31.3 minutes, which makes sense. That sounds about right. And that's our stoichiometry problem. All right. Now, last thing we're going to talk about today, real briefly, is suppose a solution in an electrolytic cell, so the same setup, had a bunch of different ions in it. What if I had copper 2 plus and silver plus and zinc 2 plus all floating around in my solution? If the voltage was initially very low and then gradually turned up over time, in which order will the metals be plated out of the cathodes? So if I had 3 different ions in there, which ones would actually become a metal first, would turn into their random metal first? And it just has to do with their reduction potentials. Okay, we look at all the reduction potentials here. See, silver is the highest, copper's next, zinc is lowest. So keep that in mind. The more positive the cell potential value, or the half reaction potential value, the more the reaction has a tendency to proceed in the direction indicated. Of the 3 reactions listed, the reduction of Ag plus occurs most easily. Okay, Ag plus had the highest number, so it's going to plate out first. Copper's in the middle, Cu2 plus, and then zinc 2 plus at the end because it has the lowest reduction potential. That's the order that they would plate out in. Silver will plate out first, then copper, then zinc. Okay, that's just kind of a little bonus question for you. All right, and that does it for this unit. That's all the slides that we're going to talk about today. Most important things, that list of reduction potentials, understanding how this works, understanding how to add them together and how you have to flip the oxidation one, and then being able to do those drawings with galvanic cells. The cool stoichiometry stuff with the electrolysis could be a question. It's not the most important thing in the world, but I think it's pretty neat. All right, look forward to seeing you all in class. Hope you learned something new today. Have a good day.